when we calculate areas, the answer could be negative. So for such a function, you see this piece out above the x-axis will be a positive area, but this one is so much bigger and it's negative. So the final answer will be a negative area. So keep that in mind, don't get scared. So the answer could be a negative number. Okay, so let's say we're going to stick with it with a simple situation like, I don't know, 0 to 4. Is that okay? The calculations for anything else but 0 here will require us to plug in something like this and take it to the third power. It will give us 4 terms, and there will be a little bit more involving to calculate, but this the same thing, all steps are the same. Is that okay? You want to change that? Do you want to change anything in the function or the limits of the area, or is this okay?
That's good.
Okay. Remember the 3 preps. Prep number 1 is delta x, 4 minus 0 over n. Prep number 2 is xi, which we know is 0 plus I delta x. So this is 4i over n. And the last prep is f of xi, or f of 4i over n if you want. So I have 4i over n to the third plus 2 times 4i over n and plus 1. Simplify fully. So 4 to the third is 64, right? 16 times 4, I cubed over n cubed plus 8i over n plus 1. So I have prep 1, prep 2, prep 3. So now area equals the limit as n approaches infinity from the sum from I equals 1 through n, base times height. That's the formula. So now I'll take the dx, delta x outside. So this is limit as n approaches infinity. Delta x is 4 over n, can stay outside. It's a constant, does not depend on I. And the sum of f of xi, these 3 terms, 64i cubed over n cubed plus 8i over n plus 1, of course, from I equals 1 through n. One of the properties of the summation notation, the first one we listed, was the sum of AI plus BI is the sum of AI plus the sum of BI plus the sum of CI plus. So we have 3 terms here. So we have to break up the sum of AI plus the sum of BI plus the sum of CI if you want. So limit as n approaches infinity 4 over n. So now we can cut back on writing if you want. You can say no and I will not. When I apply the sum to this term, I will take this already outside of the summation notation because it's a constant. If you say no, then I will rewrite it. The sum of I cubed. And you have to tell me and I'll write it again. Plus the sum of this, 8 over n. The sum of I from I equals 1 through n. The same, this is a constant in front of I. Plus the sum of 1 from I equals 1 through n. But I know that these have to disappear. This one is n, this one is n plus 1 over 2, and this one is n plus 1 divided by 2, everything squared. Where does this come from? From here, from those 4 identities. 1, 2, 3, 4 identities that we wrote a few minutes ago. And the rest is just going to be a limit in n. That's it. So limit as n approaches infinity. So the rest is just algebra. 64 over n cubed times n squared, n plus 1 squared over 4 plus 8 over n times n plus 1 over 2 plus n. So I replace these three summation notations. That's why we can only work on linear, quadratic, and cubic. Okay, next. Now I'm trying to simplify as much as possible, change this into a ratio, multiply by 4 over n, and find the limit. So this is only algebra now. So limit n approaches infinity, 4 over n. So let's see what I can do here. Can I simplify all denominators? Yes, I can. Except the n. So we have to keep an n in the denominator. There is no other way. So 2 of these will go with those 2. 4, and I get what? 16, correct. 2, and I get what? 4. Okay. So the least common denominator is n. 16 times this squared. 16n squared plus 2n plus 1. Plus. Do not simplify the n, right? Because you need an n in the denominator. So 4n squared plus 4n, and this has to be multiplied by n because it does not have a denominator. So the denominator here is n, 16 times n squared plus 2n plus 1 plus. The denominator here is n, 4 times n squared plus 4n, and plus n times n, which is n squared. Okay, collect like terms. So limit as n approaches infinity, n times n in the denominator is n squared. 4 can wait patiently. 16 at n squared, 20, 21. 32, 36, and plus 16. Just making sure, 16 and 4 is 20 and 10, 21, 32, plus 4, 36, and 16. Okay, 4 can wait outside. Limit as n approaches infinity. So I have infinity over infinity. The numerator differentiated is 42n plus 36. The denominator is 2n. I know the answer, but let's do it one more time. So this is 4. Limit as n approaches infinity from 42 over 2, because the derivative here is 42, the derivative here is 2, so this is 21. So 21 times 4 is 84. A lot of calculations, but this is algebra. We have to be careful here. Get the 3 preps, put them together, right? Take the delta x in front, and then change the summation of the 3 terms into the sum of the first plus sum of the second plus sum of the third, and also apply the property that the constant goes in front. Because that's all we know. We only know the sum of I cubed, the sum of I, sum of 1, and sum of I squared. We don't know anything else. And that's it. Okay, so now finally, the shortcut. If you remember, we determined in chapter 2, we determined the derivative of the function with, and I hope you remember, the limit as age approaches 0 from f of x plus h minus f of x divided by h. This is the formal definition of the derivative, the limit of the difference quotient. But then in chapter 3, we determined the rules, that x to the third prime is 3x squared. Same thing here. We did it a long way to understand what it means, but now we have rules and ways of determining very fast, like we had with the derivative rules or differentiation rules. Okay, so let me show you how we do this in a blink, so to speak. not exactly. Okay, first, why the area? So a few minutes ago, we looked at the area under this graph. Why would I care for the area of this graph? Assuming that this is the velocity function, and time is 0 to, let's say, 2 hours, in hours time. If I determine the area equals the distance covered by the car, the particle, etc., between 0 and 2 hours. That's why we calculate the area. Again, if this is the velocity function, to determine the distance we cover between the starting point and 2 hours later, all we have to do is calculate this area. This area is exactly the distance we covered between those 2 points. Okay, so now how to calculate the shortcut for calculating the area. But before I explain that, and we'll go back and check all those that we looked at today, we have to talk about something called fundamental theorem of calculus. It has 2 parts. But I want to talk about the one that I need right now and the other one hopefully next Monday. Okay. One part of the fundamental theorem of calculus that I need right now teaches us, so part 2 actually in your book, teaches us how to determine a definite integral. What is that? What does it mean? Okay. So remember a few minutes ago we looked at the limit as n approaches infinity from the sum from I equals 1 through n from delta x, f of xi, and we know it's the exact, no approximation symbol, exact area. Okay, a definite integral uses the same symbol, but not the Greek letter s, but a stretched s. Still the same thing. It's still the sum. We cannot use the normal s because, again, it has a lower limit and an upper limit. So we're going to use an s, it's just s that is stretched. Of course, from a to b, from f of x dx, exactly the same. It has to be written in this order, not delta x f of x, but f of x dx. And we know that delta x and the dx are the same thing. So we're not going to, moving forward, determine the limit of the Riemann sum, but we are going to calculate a definite integral, which is this. What does a and b in our example would mean? So the integral from 0 to 2 from x squared dx for our very first example. And we're going to go back and calculate the other one in a minute. So part 2 of the fundamental theorem of calculus teaches us how to determine something like this. So how do I determine it? So let me give you the theorem, and then we'll go back and calculate. Okay, so part 2 of the fundamental theorem of calculus, FTC. The integral from a to b, so this is still the sum, it's still the sigma notation, same thing, but it's stretched. F of x dx is the antiderivative. Remember the notation from the very beginning? I said, what's the big deal? What's the big deal with that notation? Here it is. If I have f of x, the antiderivative is not denoted by uppercase. If I'm given f prime, the antiderivative is denoted by lowercase f. That's the big deal for this theorem. Evaluate it from A to B, which is f of B minus f of A. So, how do I calculate that? The integral from 0 to 2 from x squared dx is, what is the antiderivative? What function I differentiate to get x squared? We did that at the very beginning tonight.